formulas to for each index for like each word. So there's like the sine formula, and then there's the cosine formula. And the sine formula, I believe, is like k over n to the power of 2I over d. And then like k would be like the index token. So like it's I am a robot. And like each word is like an index in a sentence, right? So like I would be like index 0, M would be 1, and then A would be 2, and robot would be 3. But then they don't want to just like do the positional encoding for this, because there's like more advantages for this because it's more like normalized. I don't know if that's the right word, but like within a certain value, so it doesn't like expand if you have a ton of words to like a bunch of like different numbers. So they put it with sine and cosine, because sine and cosine have kind of like a range between -1 and 1, so it's more like centralized and easier to like I guess control. I don't know if that's the right word, but yeah. And then this, it's the same thing with cosine. It's just 2I over d. And then d would be like the dimension of the output embedding space. So like how big you want your positional embedding space to be in. And then I believe I is oh yeah. So for your embedding space, you kind of have like, so let's just say d is equal to 4. That's what they use in the website. You have like so you have like four columns, right? Because the dimension is 4, and then you have I equals 0 for one space, and then it's kind of like you split it into two. So one for the sine, and then one for the cosine, and then you kind of have your k values here. So 0, 1, 2, 3, and then this of course is corresponding to the words I am a robot, and then you kind of plug the k value into here, the I, which is 0, 0, and if there was more dimensions, it'd be like I is equal to 2 and I is equal to 2. So but in this case there's only 4 dimensions, so we'll stick to I equals 0, 0, and then I equals 1, 1, and then n, I believe, oh, it's like the vocab, the size of the oh no, it's a user-defined scalars. So in the paper they use 10,000, but I think you can like set it to different things. But I think they set it to 10,000 for a reason. I'm not entirely sure why, but yeah. Anyways, so yeah, and then you just do the sine. You compute the formula using these variables plugged in, and then the advantages is that, as I explained earlier, is between -1 and 1. So like it's easier to analyze, and then so this is also like a matrix, so it's like it's quick computation, so you don't have to like do like a bunch of like computation when you're trying to like get the positional embedding. You just do it like beforehand, and then you store in the matrix, and then you can work it out from when doing the transformer. And then also like for sine and cosine, they're more similar for like, let's say 0 and 1. So like you can tell, but based on like the value of sine and cosine, like where the relative similarity between two like words are in a sentence. So if they're like closer together, these will be like more similar. If that makes sense. And then finally, there was one more point. I think. Oh yeah, yeah. Every single like different number will correspond to like a different positional encoding, so they're unique for every single value. So you don't like have similar values between two ones. So you can tell like the difference between the different words and different positions. And so that's kind of like that's why they kind of like use the sine and cosine rather than like just doing 0, 1, 2, 3, 4, 5, 6, and so on.
That was good. Yeah, and also these functions themselves are hyperparameters, so you can use a completely different function if you want. The idea behind this one is that at every periodic step, so you can measure the period of this function. This function has a specific period at which the context introduced by the positional encoding will be maximized. So then every value between the value that it starts at till the next period, it will be like decreasing sinusoidally in context, and the last one will have the greatest values. And you can change that up. The idea is just to introduce some more complexity and give it some more context. But like I said, it's a hyperparameter, so you can always modify it. All right, thank you. Does anyone have any questions about positional encoding?
Yeah, can I just check my understanding? Like, the whole idea here, right, is previously with other methods, we're sequentially going from token to token, but when we go to the transformer architecture, like in the attention is all you need paper, we're losing that positional information because we're essentially running them in parallel, right? So we had to come up with a scheme to still encode the positional information of the text.
Well,
right?
It's kind of, the thing is attention in RNNs, and I guess this is a good segue into the next part. Give me 1 second to answer your question. I'm going to stop this recording. It's going to have to work for now. Okay, so taking a step back, where's the eraser? Thanks. Taking a step back. Oh, sorry, y'all fun if I erase this? Yeah, all right. Initially, series or time series data was dealt with using the same encoder-decoder architecture. The idea is that your encoder will encode your time series data to make vectors that have more context. And you'll see this kind of in this sort of form. And it's like, okay, so let's talk about part one, right? Why not RNNs? So also y'all can spin around if you need to see this, but initially the idea behind time series data was you have an encoder which takes a bunch of words, creates some contextualized vectors, which we'll call C1 to Cn, which is each of these is a time step, and each of those could be a vector with some d dimensions. And then you have a decoder that'll decode this. And then initially we used to do encoding with RNNs, but the issue with the RNN architecture, and this is an RNN module right here, this is your previous time step contextual vector, or we'll call it memory for now, which represents a C t minus 1. And then you get your input for that specific time step as xt, or the current time step. We'll go into some activation function. Let's call it like sigmoid. It's usually tanh. I guess we could call it tanh. So hyperbolic tangent. And that gives you your hidden state, or basically your output at t. But it also gives you your next contextual vector. Now the idea is, if you imagine chaining a bunch of these, you lose context about this word when you're like 100 tokens into that sentence. So what we can do instead is we want attention on specific words or tokens that is not bound by proximity. So if you say like, the example I use here is my dog bit her tail. My dog bit her tail. Right, and we'll call this x1, x2, x3, x4, and x5. Dog here, for example, should pay attention to not only just proximity, it should not pay the most attention to the words next to it. For example, here, it should pay the most attention to something like tail or bit, because you don't know if you're talking about my or dog in the context of the sentence. And then if you say her, that should refer to the dog and not the person. So these three values should have much more contextual representation by this word than the other tokens of the sequence. So what we can do is we can use linear transformations, which is how we get the attention matrix. So let's call these x1 through xn as your tokens or your sequence, and we'll set some cap on n as like the max tokens that you can accept for your model. And then each of these xi's is a vector of, and we'll call it, for this value xi, from dimension 1 to dimension d, where d is your embedding space. Like we talked about that matrix of embedding spaces. So one way to do that, and this is like for the bigram model, the way that you would have done it is using like a one-hot encoded vector, where your d dimensions would be the vocab size. So like you have all your possible words or all of your possible bigrams. I'm not gonna write this down actually. And then you just do a one-hot vector for whichever word. So then my would be like 0, 0, 0, and let's say like there's 1 right here. And that's your one-hot vector, where this is like your vocab size. The issue is once you get to like English language, and not just bigram models, and you have like 300,000 possible tokens or more, that'll be so much information to store for each token. So instead what we do is we create or we set the value of d to some value, let's say like 30 dimensions or something, and you just initialize random values for each of those dimensional points. So you create a randomized vector in this embedding space, and then that will be your input. And later on, we'll pass it to a neural network that'll propagate or do some backprop to update the actual vector representation, so it makes an actual, like a good vector in the vector space. And that brings us to positional encoding. So not only do we have just the input embedding, we also take the inputs into an input embedding, and then into a vector sum of the positional encoding. And this is now your actual inputs to your encoder module. Also, for reference, you guys might want to pull up the transformer architecture picture, because we're going to be going through that today. So the idea is that attention extends beyond the proximity of those words or of those tokens. So positional encoding is not just enough, because positional encoding will give it cyclical randomized periods of attention or context. So what we can do instead is what we want is a function, let's call it attention, which maps from your input vectors to some contextualized vector, where this will be done linearly, so it's some linear multiplication, which we'll call the weights, and we'll call it like Wij. And the reason we have multiple indices we'll talk about. So what we can do is we can do a matmul, or matrix multiplication. And just for everyone to understand the notation, it can be like xi times xj in a dot product fashion, or if you take xi transpose xj, same thing. All right, so what we can do is we can grab all of your inputs and then do like a, let's say we take the first word. What we want is attention represented by this just first token. And the reason that this is why it's called self-attention is we take this word just multiple times, okay, and multiply this by each of the words or each of the other tokens. So this gives you some weight vector, and we'll represent it with the two indices that we use here. And this is still a vector. Like I'm drawing W, just make sure you know that it's not uppercase just yet. So it's not a matrix just yet. It's just a value at this point. So you could consider a value in a matrix, wherever you wanted to. I also wrote IJ. I meant to write 1, 1. 1, 1. And this would be W12, W13, and then so on. And then these are like your actual attentions, or also denoted O, or as in your output vectors. So what we can do is if we take, so now you have your output attention. If you multiply that attention with the original words, so you take x1 w11 plus x2 w12 plus x3 w13, and then so on, we get your contextualized vector for the first token. So now we replace, instead of like just passing this into your RNN, or your model or whatever, you can get rid of xi or x1 and replace it with the contextualized vector c1, which has more context about what words to pay attention to. And at the moment, this seems kind of arbitrary, and it's because it's randomized embeddings. But when we go back and do backprop, we'll update those so it makes more sense. So giving it kind of like a linear or like a model architecture type of visual, I'm gonna redraw this. I'm gonna redraw this. As a bunch of modules. Also, is this fine if I erase this? Okay. So if y'all want me to pause it anytime, like let me know. What we can take is all of those input words, like we said before, x1, x2, x3, dot, 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 and we can do a matrix multiplication, or that dot product that we talked about. We take all of these inputs, and then we query it. This is where the Q vector comes in, the query matrix. And we query it with, let's say, x3, or actually let's do x1, just for simplicity. Then we get a bunch of these intermediate weights that we talked about. We represent them as W11, but we want to scale them later on so that it's distributed from 0 to 1. So what we'll do right now is I'll create the same ones that we talked about before, except call these like with a tilde. And these are passed into a normalization, which is also a linear transformation. So can everyone see this? That's good. Norm. And here we get our actual W11, W12, and W13, and so on. Now this finally is our actual attention values. So this, what we'll do is we'll actually matrix multiply with these again. And I'm going to redraw these up here. X1, X2, X3. And then you're going to do let's call it dot product. So binary multiplication with each of these. And then all of these will go into, so that is a matmul right there. Actually, this multiplication right here. So I'm gonna just draw that with the matmul block. Okay. Now from here, we actually get our output, which is C1 through Cn, so the contextualized vectors for each of those tokens in the sequence. So this right here, the idea is we want to make something trainable out of this, and this is all linear combinations or linear transformations. But what we can do is consider that we can, because each of these are vectors, xi is equal to that xi at 1 to xi at d for d dimensions. What we can do is we can see that for any xi dot product with some matrix where this is 1 by d and this is d by d, we get some vector which also is 1 by d. So we can create matrices for each of these, and also maybe this is what I should point out. We're passing this x1 in. That is the query that we talk about when we talk about QKV vectors. This is the query vector. These are all the key vectors, and we multiply them with the original ones. They're called the value vectors. So in reality, it's Q, K, V, but K and V are always equal to each other because we just pass them in. We pass in keys initially to create weights, and then we multiply them with the keys again, or the values, to get contextualized vectors. So These are also sometimes called outputs, or O. So you might read a paper or something that says the QK circuit, which is this part right here. It's the QK circuit. And then the OV circuit, which is the O times the V is this circuit, which actually creates the contextualized vectors.
Okay, and after this is trained, what we've extracted or achieved is we're essentially learning to what degree are x2, 3, and 4 relevant to x1, say, and for each given token, how are other tokens relevant to them?
Yeah, pretty much. And the way that we train them is we want to create trainable weights. And that's where this matrix comes in. So we'll create a matrix for each of these QKV. We'll create MQ, MK, and MV. Right now, they're pretty arbitrary. They're pretty much identical at the moment. And when we come back, we'll train them again. What we can do is, because we're passing these in as keys, we can multiply each of these vectors by MK. MK, right there. So each of those results in the same dimension. So the dimensionality is still the same. But we're creating trainable matrices that when we backpropagate, we can update these to change the values of the actual vectors, but still keep the same dimension.
Okay.
And then what we'll do is the same thing for the keys, the query with MQ in this situation, and the values, which we'll do MV. Now we can represent it linearly or with linear transformations, like we've been doing. So I'm gonna give y'all like the actual self-attention block. I guess I'll do it over here.
Okay, how do we extract general patterns from these trained matrices? Because like from one sentence to the next sentence, how the dependency between words, like it's case by case, it's like sentence to sentence. So
Sorry, what do you mean?
so like if I say like I am a robot versus, you know, my dog bit her leg or
Yeah.
whatever, like in each of those sentences for each given token, the relevance of other tokens that are nearby or further away is unique.
Yeah.
So what is in the matrix that somehow enables me to now put in any sentence and still these context matrices help know what to point to?
So that's a good question. So the idea, let's talk about backprop, right? So when you're backpropagating some values, because all linear transformations, you're still allowed to backprop through the entire thing. We'll get values for each of these MK, or like all of these matrices. Plus we'll get backprop values for each of these inputs or the actual queries and the keys. So what that means is like, have y'all seen the micrograd like backprop tree?
Yeah.
So this is a multiplication right here, right? So if you have the multiplication x1 and mk, and this is your multiplication. I forget what actually happens, but it's like you have your gradient or your flow gradient that gets distributed. I'm pretty sure the multiplier is a gradient distributor.
I get how the backprop works, but like, is what we're ultimately learning just how in general, say, English sentences, typically words are relevant to each other at some typical distance?
Yeah, so we're learning, like we're parallelizing the learning. What we're doing is for X1, right, the actual inputs, we're learning better embeddings because these were initially randomized.
Yeah.
So we're learning better embeddings that when we visualize them, what we should see is like in this embedding space, like what we talked about before, hello and hi as vectors should end up very close to each other because they're using the same context. So their contextual vectors should be the same. So when you backprop those values, xi, or these inputs, should end up in the same vector space for embeddings. Then the matrices mk and mq, those are learning, or those are being updated so that they learn to better assign vectors. So when we multiply mk with x1, right, nk will give it some linear transformation that modifies the vector. So mk over iterations will learn to change that actual x1 vector to be a better representation of that specific key or that specific query.
Gotcha. Okay.
So
makes sense.
Okay, that's good. Also, yeah, like I said, if anybody has questions, stop me, because I know I'm going fast. Okay. So now for the like model architecture representation of it, you have your sequence of inputs, x1 to xn, where again, x1 is a vector of d dimensions. We're gonna pass this into 3 separate things, and we're gonna call these linear nodes or modules, where this one can be like xi times, let's say mq. So this will be the query linear module. And then this will be a linear xi times mk, which will be the keys linear module. And this will be xi times mv, which would be your values linear module. Okay. Now, like we said before, I'm gonna bring this down here because this is way too high up for intro. Mat mul, these 2 values. And what do we get here? Mat mul, that gives us these intermediate values. So what do we do now? We have to norm and scale them, or just norm them in this situation. Also, does everyone understand what norm does? It distributes it from 0 to 1. So now if you sum up all of these weights, you'll get a value of 1. Okay, and then from there, you're going to take the values and the norm, and then matmul these to get your contextualized vectors. Okay. So does everyone understand this so far? Okay, because now we're going to go into multi-headed attention. So the initial idea is that this word, right? My dog bit her tail. Each of these has significance, and each of these words will have some attention to that points to something else, right? So we should be able to represent each of these attention mechanisms as separate attention modules. So we can identify multiple heads for that module. A perfect situation would be where we have a head for every single token in our vocab, but that takes up way too much computational power. And that will also overfit because it would just memorize the hidden states for each of those. So what we do instead is we create heads. And what we specifically mean by heads is we parallelize tasks. So instead of just one linear, we'll multiply this by some h heads and create h of these in parallel. And then so what we get from here is when we actually do the linears, and then we do a matmul here, what we get from here is instead of just getting one weight, we get weight ij from the first head down to weight ij for the h head. Okay? And then once we norm it, also these are the tilde ones. And then we norm, and then now we get weight ij from the first head to weight ij of the last head, h. So finally, when we matmul this as well, instead of this, what we'll get is this vector, like this entire sequence with contextualized vectors for each word or each token. We'll get those for each head. And we don't really like having more like a matrix representation. I guess this is a tensor because it's like a vector inside of a vector inside of a vector. We don't like having extra dimensions on top of or we don't want to have more dimensions than our actual input. So our output should not have more dimensions than our input. So what we do instead is we take all of this and then we concatenate it. So concat is just like you think it is. You just append these vectors together. And then here you pass it into your, some people call it dense, but dense makes it sound like it's like an actual neural network. Think of it more just like a linear transformation. And using linear transformation, we can determine how many dimensions we want as our output space. So what we'll do instead is we'll just create contextualized vectors. And also you can determine how you want these to be done. And we'll call this the final contextualized vectors. So that's multi-headed attention.
How many heads would be optimal, and is it like user defined or?
Yeah, it's a hyperparameter.
I see.
Yeah.
But is there any guidance on like how many should we use?
So there is a notebook called Tensor to Tensor, which you can take a look at, and that'll show you the representation of each word with each of its, one word's attention to all of its other words from the input and output, and you can modify which head you're looking at. Like from an overarching perspective, I don't think there's like an actual specific value. I think it depends on your space. Because at this point, we're diving so far in that it's basically a black box. You can't know exactly which specific part of this is causing this issue.
I see.
So that's one thing.
So like in actual training, do we just like test by?
Fuck around and find out.
Yeah.
I think that's a good way to approach it. I think another thing would be taking a look at other papers. I think in the attention is all you need paper, they do 6 heads, I think,
Eight, yeah.
or 8 heads, because there's multiple places where you can parallelize stuff. So you can parallelize the number of heads in your multi-headed attention. But if you look at the module, you can also create multiple encoders.
Oh, right.
So you can do n encoders, h heads. So now you end up with n times h total multi-headed attention values.
Oh.
So at that point, how do you know if you're tweaking the right value, right?
Yeah. Fuck around by that.
Yeah, pretty much. So does anyone have any questions about this part? Because that's pretty much it. That's pretty much it for multi-headed attention and attention in general. After this, we're going to just be breaking apart the encoder and decoder like parts of the transformer.
They should have called this the Hydra architecture instead.
Hydra architecture. I think there is something like that. I've heard that somewhere. Hydra architecture. I think Will was like joking about it. I don't recall. Yeah, what's up?
You said like you would call this last part linear instead of dense. But
Yeah.
Are they functionally the same?
Yeah, I mean, if you think of a linear function is a bijection. Do you know what a bijection is? It's like a one-to-one mapping of each input to output, and it's also one-to-one and onto, as in like it's mapping from one space to another space. Dense layers are fully connected. That's why they're called dense. So it's the same thing. Like if 2 layers are fully connected, that is a linear projection or a linear transformation. I should say, not a projection. Linear transformation, which is the same thing as a dense modification or a dense layer. Yeah. So you can think of each layer as like your first layer as your domain, your second layer as your codomain. And that. Yeah.
Like, do we run all of this n times for like every single word?
No. Well, so these words are passed in as vectors. So you're technically doing matrix multiplications.
So do it at once?
Yeah, so you do it at once. If you're talking about like per word, you do all the words at the same time.
Yeah.
The one issue or the one thing that you'll have to deal with when you're actually programming it is the query, because the query you do one word at a time.
Yeah, that's what
So you might want to parallelize those and find the query values first, and then pass them in, and then backprop it after, instead of like backpropping at each query value. Yeah, we actually haven't talked about backprop yet because we haven't gotten a neural network, which is another part of the encoder. What time is it, by the way? How much time do we have left?
5 minutes.
We have 5 minutes? Okay, I think that's it for now. Next week we'll talk about encoder and possibly decoder. Decoder is a little bit more confusing because it has to do with like next word prediction. So we talk about like the actual generative model. So I think we'll just end it here for today. I would say for the next few weeks, if you want like practical application, take a look at week 6's implementing GPT-2, the Andre Karpathy video, and just try starting on that. And that'll probably give you a good idea of what we're doing. All right.